In this video, we're going to talk about inequalities, including how to recognize inequalities and how to solve inequalities that are linear or that involve absolute values. Recall that in mathematics, an equation is something like this. That is to say, two algebraic expressions which are separated by an equal sign. An inequality, on the other hand, is two algebraic expressions that are separated not by an equal sign but by an inequality sign, like the less than or equal to symbol, or simply the less than symbol, or the greater than symbol, or the greater than or equal to symbol. Inequalities arise often in mathematics, and it is important to be able to solve them. Just as solving an equation means finding all values of x that make the equation true, solving an inequality also means finding all values of x that make the inequality true. And one difference between equations and inequalities is that inequalities will tend to have infinitely many solutions. Let's dive right in and try to solve the inequality that was just on the screen. This is an example of a linear inequality because the expressions on the left and right-hand sides are simply linear expressions of the variable x. And to solve this inequality, we can use techniques that we use to solve linear equations. So we might begin by adding 1 to both sides of the inequality, and then by dividing both sides by 2. And just like that, we have the solution of the inequality. The values of x that make this inequality true are all values of x that are less than or equal to 3. In fact, it's convenient to express the solution using interval notation, so we would say that the solution set of this inequality is the interval from minus infinity all the way to 3, where the endpoint 3 is included in the interval. Let's have a look at another example. This is an example of a double inequality, where one expression contains two inequality symbols. The goal here is to find all values of x such that 4 minus x is greater than 1, and such that 4 minus x is less than or equal to 7. And therefore, the way to proceed here is simply by splitting this double inequality into two separate inequalities. Once again, we want to know when 4 minus x is greater than 1, and when 4 minus x is less than or equal to 7. So we'll simply solve those two inequalities one at a time. Let's deal with the inequality on the left first. We can begin here by adding x to both sides to get 1 plus x is less than 4, and then by subtracting 1 to attain x less than 3. So this, or to be more precise, the interval from minus infinity to 3 is the solution set of the first linear inequality. Turning to the second linear inequality, we can subtract 4 from both sides to get minus x is less than or equal to 3. And now multiply both sides of the inequality by negative 1. And careful, anytime you multiply an inequality by a negative number, you need to reverse the inequality symbol. So multiplying by negative 1 will give us x is greater than or equal to negative 3. So the solution set of the second inequality will be the interval from minus 3 to infinity. Now, what's the solution of the original double inequality? Well, the key is to remember the mathematical meaning of the word and here. Indeed, the word and is telling us to take an intersection, right? Because we need x values to belong to the solution set of the first linear inequality, the one on the left, and to the solution set of the second linear inequality on the right. So the final answer will be obtained by computing the intersection of our two solution sets. And the intersection of the open interval from minus infinity to 3 and the half open interval from negative 3 to positive infinity will be the half open interval from minus 3 to positive 3. That is the solution of the original double linear inequality. Let's move on and take a look at what it means to solve an inequality that contains absolute value brackets next. We're going to begin with a very simple example, namely the inequality, the absolute value of x is less than 1. To get a feeling for how this inequality works, it's helpful to recall the definition of the absolute value. Recall that we can define the absolute value of x as the distance between x and 0. So let's take a look at a number line and mark the point 0 and understand where x can be if it's going to make this inequality true. Well, if the distance between x and 0 must be less than 1, it means that we can move up to 1 unit to the right and 1 unit to the left to -1. And x will be forced to lie somewhere in between -1 and 1. This, therefore, gives us our solution. The solution will be the open interval from -1 to 1. Let's look at another example and try to reason about it in the same way. Our next example asks us to solve the inequality absolute value of x minus 2 is greater than or equal to 1. Again, if we think about the absolute value in terms of distance, we should remember that the absolute value of x minus 2 represents nothing other than the distance between x and 2. So this inequality is telling us that the distance between x and 2 must be greater than or equal to 1. So let's think about it. Let's mark the number 2 on a number line, and then see what it means for the distance between a point on the number line and 2 to be greater than or equal to 1. Well, it clearly needs to be beyond a value of 3 from 2, right, off to the right, or moving a distance 1 away from 2 in the other direction, it needs to be beyond the number 1 to the left. And therefore, we once again obtain a solution. The solution this time will be a union of two intervals, namely the union of the interval from -infinity to 1, including 1, and the interval from 3 to infinity, including 3. Right? And all that means, once again, is that if x is chosen to be somewhere here, or perhaps somewhere here, then its distance from 2 will be less than 1, so it can't be in the solution set of the inequality. Only when x belongs to this piece of the number line or to this piece of the number line on the right will it satisfy the condition that its distance from 2 is greater than or equal to 1. Having looked at a couple concrete examples, let's summarize the solution sets of a few important types of inequalities that involve absolute value brackets. In general, an inequality of the form absolute value of x is less than a, where a here is just a positive number, will have a solution set that consists of the numbers in between -a and a, right? Because those are just the numbers whose distance from 0 is less than a. So the solution set here, using interval notation, would be the open interval from -a to a. If the inequality symbol is a less than or equal to symbol, then it simply means that we will be dealing with a closed interval instead, because now the numbers a and -a will belong to the solution set. So the solution set of the inequality absolute value of x is less than or equal to a will be the closed interval from -a to a. If we reverse the inequality symbol and consider the inequality absolute value of x is greater than a, then the solution set will become a union of two open intervals, the interval from -infinity to -a union the interval from a to infinity, because those are precisely the real numbers whose distance from 0 exceeds a. And finally, if that inequality symbol turns into a greater than or equal to symbol, then once again we simply include the numbers a and -a in our solution set. These solutions are not solutions that you should blindly memorize. Keep in mind that you can always reason them out simply by recalling the definition of the absolute value and relating it to distance as measured on the real number line. Let's finish up by taking a look at a more complicated example and seeing how the ideas that we just discussed can help us solve it in a systematic way. What we'd like to do here is solve the inequality the absolute value of 2x minus 3 is greater than 9. To understand how to proceed, let's go back to our list of general inequalities involving absolute values and take a look at the third item in the list. Notice that the solution of the inequality the absolute value of x is greater than a consists of all numbers x that are less than negative a or greater than positive a. The inequality we're being asked to work with has the same basic form, right? It's the absolute value of something being greater than a constant. And therefore, that something in between the absolute value brackets, namely 2x minus 3, must either be greater than 9 or less than negative 9 in order for the inequality to be true. Therefore, our approach is once again to divide and conquer. We're going to take an inequality and split it into two separate linear inequalities. It only remains to solve each linear inequality separately, which we can do quite easily. So beginning with the inequality on the left, we have 2x is greater than 12 after adding 3 to both sides, which gives us that x is greater than 6 after we divide both sides by 2. So the solution here will be the interval, the open interval from 6 to infinity, right? That's how we describe all numbers that are greater than 6. Then moving over to the right, we can add 3 to both sides of the inequality once again to obtain 2x is less than negative 6, so that x, after we divide by 2, must be less than negative 3. So the solution set here will be the open interval from minus infinity to negative 3. Finally, we need to remember that the word or is asking us to take a union of our two solution sets, so that the final answer here and the final solution of our original inequality will be the union of the interval from minus infinity to negative 3 and the open interval from 6 to infinity.